Toxicological Chemistry, Lecture Number 2. Preliminary examination of research objects, methods of chemical toxicological analysis, chromatography and spectroscopy methods, screening analysis of poisons. In case of suspicion of poisoning from any substance, the relevant corpse material of the deceased shall be taken as material evidence for forensic chemical examination. Material evidence sent for investigation is determined in each case by the nature of the alleged poisoning. At least 2 kg of internal organs are removed from the corpse from an adult. It is strictly forbidden to wash the material evidence with the water, contaminate it with chemical and mechanical mixtures. When poisoning with an unknown substance is suspected, the following internal organs are collected separately in appropriate glass jars: gastric with capacity, small and dense intestines, 1 meter long from each other with a capacity, 1/3 of the liver with more full of blood, and gallbladder with capacity, 1 kidney and all of the urine, 1/3 of the brain, heart with a holding blood, spleen, 1/4 of the lungs rich with blood. In addition to the above material evidence, in case of suspicion of poisoning by injecting the toxin into the uterus, rectum, subcutaneously and intramuscularly, in addition to the forensic chemical examination, the uterus and rectum should be used as material evidence. In addition to the internal organs sent in separate glass jars during the forensic chemical examination of the exhumed corpse, the following material evidence is added to the forensic chemical examination. Soil samples taken from 6 areas of the grave and weighing 1 kg each directly under from the coffin and from the top side, 2 from sides and 2 from edge areas. Items in the coffin, wooden parts under the coffin are also sent for research. Corpse parts, internal organs, and other material evidence are sent to forensic chemical analysis in clean, dry, and white-necked glass jars, each separately. The use of metal or pottery for the purpose should not be allowed. In the practice of chemical toxicological analysis, canning of research objects is generally prohibited. However, if the transportation of internal organs takes place in the summer and it takes more than 3 days, then the object can be canned. Only purified ethyl alcohol is used as a preservative. If poisoning with ethyl alcohol and nitrates is suspected, the object should not be canned. At the time of canning, the height of the alcohol layer on the inner members of the jar should not be less than 1 centimeter. In addition to the canned internal organs, a control sample of up to 300 milliliters of the alcohol used for canning should be sent for forensic chemical examination. After canning of biological materials with alcohol, glass jars are closed with a tight glass stopper wrapped in clean paper, wrapped with a strong rope, sealed with a screw seal. A paper label is pasted on each jar. The number of the jar, surname, name, and father's name of the deceased, name of biological material, number, and date of the act of forensic examination of the corpse. Surname of the forensic expert who examined the corpse should be indicated on the label. In many cases, the examination of research objects or a simple visual inspection raises a certain possibility as to which substance caused the poisoning, and it allows to take the appropriate direction for further purposeful chemical toxicological analysis. Preliminary inspection of research objects clarifies the next direction of chemical toxicological analysis and provides valuable information about their appearance, odor, color, reaction type, pH, as well as the presence of foreign bodies and preservatives. External features and characteristics of the objects. When examining examining the internal organs of a corpse, it is first necessary to determine which organ and which part of it is included in the analysis. If the object is in liquid form, it is determined to be transparent, volatile, viscous, and mobile. In powdery objects, the substance is investigated as amorphous or crystalline, and the shape and size of crystals. The smell of the object. The specific characteristic smell of the material evidence provides very valuable information for the chemical expert about the substance that causes poisoning and can guide the future cause of chemical toxicological analysis. For example, the smell of almond seeds in the stomach makes you think about the possibility of cyanide poisoning. The characteristic odor of pyridine bases in the gastric contents indicates denatured alcohol poisoning. The characteristic irritating odor of sewage oils, the specific odor of phenol adds. The detection of odors specific to such other substances raises the question of poisoning by those substances. Detection of internal organs as well as odors of the stomach is carried out when object of study is not rotten. If the biological material is subjected to decay, the characteristic odor of the poisonous substance is covered by the smell of decayed products, hydrogen sulfide, ammonia, and ads. In this case, no auxiliary assistance or direction is obtained due to the smell of the object. The color of the object. The color of the biological material, especially the capacity of the stomach, is of some importance in assuming a first impression of the substance that caused the poisoning. The yellowing of the biological material suggests that it was poisoned by picric acid, chromatase, acrylic, nitric acid, some aniline dyes. Blue biological material is a reason to think about copper salt poisoning. Poisoning with arsenic compounds can be assumed when the biological material is emerald green. The black color of the gastric mucosa suggests the possibility of poisoning by solid sulfuric acid. The pink color of the stomach indicates poisoning from erosin-stained Suleimani tablets. The purple color of the biological material indicates the use of an ink. From the experience of foreign chemical examination, it is possible to draw a large number of facts that the appropriate colors of the biological material allow to accurately determine the cause of poisoning. Determination of preservative. As mentioned above, in some special cases it is necessary to preserve biological material, and only pure ethyl alcohol is used as a preservative. The fact that preservative is detected during the initial inspection of the object is very important. This is because many subsequent chemical operations are incompatible with the presence of a preservative and require its removal. For example, in order to investigate the cause of metal poisoning, it is not possible to perform the method of mineralization with solid sulfuric and nitric acid in the presence of alcohol. So it is necessary to first remove the alcohol. If the biological material under examination has been canned with ethyl alcohol, this is usually recorded in the forensic report of the corpse. In some cases, such registration is not noticeable. If there is no alcohol control sample in addition to the canned biological material entering the chemical toxicological laboratory, the chemist expert draws up an inspection report of the research object and indicates that there is no control sample of the preservative. This act shall be sent to the relevant bodies that send the object for forensic investigation of research. Also, very rare, sometimes it is possible to preserve biological material sent for chemical toxicological analysis with formalin, phenol, glycerin, and other substances. Preservation of biological material with these substances prohibited. Because formalin and phenol themselves are poisons, they are included in the list of poisons whose chemical examination is mandatory. On the other hand, formalin, which is included in the study as a preservative, complicates and hinders the chemical and toxicological analysis of many toxins. For example, forensic chemical evidence for methyl alcohol, methanol, is based on its oxidation to formaldehyde. Therefore, the presence of formalin as a preservative in biological material prevents the proof of methyl alcohol. Formalin also causes the breakdown of a number of other toxins, for example, ammoniac, hydrogen cyanide, and makes it impossible to find and prove them. Therefore, before starting the chemical toxicological analysis, it is necessary to know: does the research object contain preservatives, and if so, which one? If the forensic chemical laboratory includes biological material, cannabis, formalin, phenol, and other substances, the chemist expert must draw up an act on volatility of the rules of sending chemical objects for chemical toxicological analysis and send it to the forensic investigation department for the appointed chemical examination. Identification of foreign things, foreign bodies. Incoming research objects are examined very carefully, first with the naked eye, then with a magnifying glass, and then with a microscope. In this case, some foreign bodies and impurities can be found in the object of research: arsenic oxide, specific porcelain granules or sediments, prismatic crystals of strychnine nitrate, seed of poisonous plant, and other plant particles. All suspected foreign bodies are removed with clean tweezers and examined separately. In the study of extracted seeds, plant and fungal particles, as well as other foreign bodies of plant origin, expert advice is needed, and if necessary, these objects are well studied by pharmacognosists. Determination of pH. Determination of the pH of biological material has great importance for the detection of toxic substances. By setting the pH, the volume of the chemical toxicological analysis can be shortened or expanded. The pH of biological material is usually determined by various indicators. For example, lakmus, Congo red, phenolphthalein. These indicators are often used not in solution, but in the form of impregnated filter paper. The reaction of the condition is determined by the paper on which these indicators are included. The exact pH of the biological material under study was not determined. A universal indicator paper can solve this problem. Therefore, the determination of the pH of a biological material with a universal indicators paper is considered to be superior to filter paper impregnated with litmus, Congo red, and phenolphthalein solutions. To determine the pH of the biological material, a small amount of the test object is finally chopped with scissors placed in a test tube. The appropriate amount of neutral purified water is added, and the test tube should be shaken well. The aqueous extract is separated from the solid particles of the biological material. The acidity and basicity of the tube are determined with the help of indicator papers in the obtained aqueous extracts. The first tests are based on litmus paper of different color. Two porcelain plates are taken, one with blue and the other with the red litmus paper. A drop of aqueous extract is added to both papers through a glass rod. The acidity or basicity of the environment is determined by the change in the color of the indicators. The acid reaction of biological material is because of the presence of the following components: mineral acids, organic acids, natural acid composition of the organism, for example, gastric juice, vomit mass. Next, acid fermentation, easily hydrolyzed salts of strong acids. It is advisable to use red Congo paper to distinguish these acidic components. The fact that biological material has an alkaline reaction according to litmus paper indicates that it contains our following substances: caustic alkalis, carbonate and soluble silicate salts of alkali metals, ammonia, salts which include either hydrolysis of weak acid and strong bases, alkaline fermentation. The methods used in toxicological chemistry are based on the natural and specific features of the subject, which tasks solved by. Thus, the chemical toxicological study of various biological materials for this toxic substance consists of several stages, as described above. Taking into account the above, the methods used in toxicological chemistry can be divided into the following groups. First, 1. Methods of isolation of the studied toxic substance from biological material. Methods for removing toxic substance from foreign impurities and which isolated from biological material. Methods for identification of isolated toxic substance as a qualitative detection. Methods for quantification of isolated toxic substances. Isolation methods are often great importance for chemical and toxicological analysis. Only properly selected and properly performed isolation methods can guarantee objective results of chemical toxicological analysis. Isolation of a toxic substance from a biological material depends primarily on the chemical nature and properties of the substance. The following isolation methods are available. Method of isolation by distillation with water vapor. In this way, volatile and easily evaporating organic substances are isolated. Next, isolation method by extraction with acidified water or acidified alcohol. In this way, alkaloids and many synthetic organic substances are isolated from biological material. Next, isolation methods by extracting with various organic solvents. In this way, chemical poisons, for example pesticides, are isolated from biological material. Next, methods of isolation by decomposition or mineralization of biological material. Metal poisons as well as arsenic compounds are isolated from biological material by this method. Next, isolation method by extracting with water. In this way, toxic acids, alkalis, and their salts are isolated by this method. As can be seen, in most isolation methods, the object of study is extracted with different types of solvents so that the main substance passes from the biological material to the liquid phase. The process of isolating the main substance from the biological material is a multi-stage process. The main stage of this process are penetration of the solvent into the tissue and cells of the corpse material as well as other objects. Next, solubility of the target substance in the solvent or interaction of substance with the solvent in the tissue and cell of the biological material. Third, transport of the dissolved target substance through the cell membrane to this intercellular space. And last one, mixing of the isolated substance with the main mass of the solvent. The degree of isolation of the substance from biological material depends on several factors. For example, the solubility of the isolated substance in the solvent, the structure of the biological material, porosity, the ability of the solvent to penetrate the tissues and cells of the biological material, the fineness of the biological material, the intensity of mixing of the crushed biological material and solvent, the number of extracts from the biological material with the solvent, from the temperature regime, from the pH of the solution, and its. The target chemical isolated from the biological material is not homogeneous at all and consists of many mixtures. Various impurities, fats, proteins, trace elements prevent the disclosure and quantification of the main substance. Therefore, the material isolated from the biological material first must be cleaned from the impurities. The following methods are used for the purpose. Sedimentation method. In some cases, the target substance and in other cases, external mixture are separated by precipitation method using the appropriate solvent or effective reactive agent. Extraction and re-extraction methods. Extracting is the process of extracting the relevant substance from various objects with a solvent. The object from which the relevant substance is extracted may be solid or liquid. Depending on this, there are two types of extraction: extraction in solid-liquid system, extraction in liquid-liquid system. Various organic solvents and water are used as extracting solvents when extracting a substance by solid-liquid extraction. In the practice of chemical toxicological analysis, the method of extraction in the solid-liquid system is mostly used on the extraction of the studied substance from solid objects, isolate them, such as corpse material, plant raw material, soil, etc. These methods of extraction can also be used with the same success to remove impurities from the test substance. The most convenient way to remove impurities is using liquid extraction. Liquid extraction is the process of distributing a solid between two immiscible liquid phases. One of these phases is often water, and the other is an organic solvent that doesn't mix with water. Therefore, the chemical studied in the liquid extraction method is extracted from the water phase to the organic solvent phase. The chemical can also be extracted again in the opposite direction. Extraction of a substance from the organic solvent phase to the aqueous phase is called re-extraction. Both liquid extraction and re-extraction methods have been used with great success in the practice of chemical analysis of substance to remove impurities. More information on extraction methods is available from the course of analytical chemistry. Absorption methods. Adsorption method, in many cases, impurities are adsorbed with appropriate adsorbent and removed. Such adsorbents include activated carbon, artificial resin, and others. Method of expulsion or evaporation. This method mostly used for easily evaporated and volatile substances, for example, for clean barbiturates. Different chromatography methods. Purification of a chemical substance from impurities can be carried out by several variants of chromatography methods. The most commonly used are molecular tube chromatography methods on a thin layer of sorbent and adsorbent. The advantage of this thin layer of chromatography, TLC, is that it is not only complete to remove the chemical from impurities, but also makes its detection reliable and accurate. Dialysis methods. It is used in chemical toxicological analysis of mineral acids, alkalis, and their corresponding salts to get rid of impurities. Microcrystallization. It is used to remove a very small amount of an individual substance from the mixture. Detection methods. Numerous methods are used to detect a toxic substance which is isolated from biological material and determine its correct identity. These methods must have a sufficiently high sensitivity, specificity, and proving ability. Classical descriptive macroanalysis reactions are not used in the practice of chemical toxicology analysis because their sensitivity doesn't meet the high requirements. Therefore, in toxicological chemistry, primary preference is given to microchemical reactions. The following descriptive methods are most commonly used. Droplet reactions. As it is known from the course of analytical chemistry, the reaction is carried out on a glass or porcelain plate as well as on filter paper using both the test substance and drop of reagent solution. Droplet reactions are very sensitive and quick to perform. Microcrystalloscopic reaction. The detection of a substance is determined by the shape, size, and color of the crystals formed as a result of their interaction with the relevant reagent. These properties of the crystals are very important features for chemical toxicological analysis. The detection of many substances in the practice of chemical toxicological analysis is based on microcrystalloscopic reactions. Microdiffusion methods. The way to do these methods carried out in a special conveyor bowl or similar bowl. Inside the container there are two chambers for microdiffusion, an inner circular chamber and outer annular chamber. The test objects, blood or urine, is placed in the outer chamber. and the reactive solution of a preparate solvent is placed in the inner chamber. The dish is closed with a special lid and stored in normal room conditions for several hours. From the test object, the volatile substance first passes into the cavity of the vessel and then into the reagent solution of the preparate solvent that interacts with that substance. The advantage of the microdiffusion method, it is possible to detect small amounts of volatile substance in the object. Chromatography method. The method of chromatography of a solvent on a thin layer is widely used in the practice of chemical and toxicological analysis. The method is performed relatively quickly and gives accurate results. This method is widely used for the proof of barbiturates, alkaloids, glycosides, synthetic chemical compounds, and other substances, and it has a great importance. In some cases, two-dimensional chromatography is also used. The study of volatile poisons using gas chromatography is very widespread now. Spectroscopy methods. Spectroscopy in the ultraviolet and infrared fields has a great importance for the detection of matter, where an IR-Spectroscopy, the test substance, as well as the expected standard sample, are extracted and compared using special devices. Depending on the nature of the spectrum, the detection and identification of the substance is carried out with high confidence and accuracy. Biological or pharmacological tests. If there is any doubt in the detection of some toxic substances, in the condition of chemical toxicological analysis by the mentioned methods above, additional pharmacological tests are carried out in order to fully identify these substances. Such substances include strychnine, atropine, nicotine, hyoscyamin, and ads. Quantitative determinant methods. Great attention is paid to determining the amount of substance detected through chemical and toxicological analysis. Thus, in some special cases, only the similarity of the results of quantitative analysis and qualitative analysis allow the forensic authority to conclude that the substance is poisoning. Therefore, the quantitative determination of the substance, which found out during the chemical toxicological analysis, is mandatory. High sensitivity and accuracy methods are needed to determine the amount of toxic substances which isolated from biological material. First of all, the optical methods can be shown: nephelometry, photocalorimetry, spectrophotometry. Different chromatography methods are also used. Chromatography on thin layer absorbent (TLC) or paper chromatography, ion exchange chromatography, gas chromatography, gas-liquid chromatography. Recently, a combination of two or more methods is being developed: extraction photometry, chromatophotometry, chromatospectrophotometry, mass chromatography, chromatodensitometry. Chromatography is a method of separation, division, identification, and quantitative analysis of the components of mixture based on their different distribution between the two phases: active or mobile and passive or stationary phases. In other words, chromatography is a method of transporting substance with the help of mobile phase and individualizing them by repeatedly subjecting them to absorption and desorption as they pass through stationary phase. Chromatographic separation of complex mixtures is depending to the different sorption capacities of the components from the mixture. Chromatography is a physicochemical method, a dynamic process that is one phase always moves relative to another. In the process of chromatography, the moving phase, the element which contains the sample analyzed, passes through the stationary phase. In this case, as a result of repeated sorption and desorption processes between the sample and the stationary phase, the distance traveled by the components of the sample in the direction of flow are different, which ensures effective separation. Chromatography can be viewed as a science, as a process, as a method, as a system, along with the separation of substances by mooring two non-mixture phases relative to each other as a result of intermolecular interactions. In chromatography, in some literatures, mobile phase is also referred as a mobile phase, the eluent or a carrier phase. Mobile phase can be in the form of liquid, one or more solvents as homogeneous mixtures in different proportions, or gas, helium, nitrogen, argon, hydrogen, and air. The passive or stationary phase may be a solid sorbent or a fixed sorbent on a stationary non-volatile liquid applied to the inner walls of the column. There are some features that are different for chromatography from other analytical methods. These are due to the coordination of thermodynamic and kinetic aspects due to the formation of equilibrium between the phases and the movement of components at different speeds, multiple repetition of acts, sorption, desorption, precipitation, dissolution, evaporation, dissolution, extraction, re-extraction, and dynamic conditions of component separation. Classification of chromatography methods. There are various classifications of chromatography methods in the literature. Chromatography methods are applied to the mechanism of division, the relative mobility of the phases, the technique of implementation of the methods, the state and purpose of the aggregate mobile phase, the principle of the mechanism of diffusion resulting from the interaction of sorbent and sorbat are divided into different classifications according to their characteristics. The efficiency of the division, the possibility of division, and the selectivity of the division are the main parameters for evaluating the TLC process, thin layer chromatography process. The effectiveness of the division, the effectiveness of chromatography separation depends primarily on the correct assessment of the conditions, the correct choice of solvent system, detector, the correct implementation of the technique. The efficiency of splitting in TLC balls is determined by the number of theoretical plates and the height of equivalent to the theoretical plate. Resolution or degree of division, the possibility of dividing two chromatographic fields is determined by the ratio of the distance between the centers of the air spots to have the average mathematical sum of their weights. One of the main parameters of the TLC methods is the rate of retention or retention factor, RF. Sample components are transported by mobile phase and collected in any area according to their distribution coefficient when passing through the sorbent layer. The location of these areas is characterized by the factor RF. The distance from the starting line to the center of the sample spot divided to the distance from the front line to the distance to the line. Glass, aluminum, or polymer plates used as a sorbent and thin and even layer are used for TLC analysis. Most often, balls with a length of 15-20 cm, a width of 4-20 cm, and a sorbent thickness of 0.25 mm are used. For the preparatory TLC, balls with a length of 30-40 cm, a width of 40-50 cm, and sorbent thickness of 1.0 mm are used. Aluminum and polymer-based balls are more practical than glass balls as they can be cut to any size with scissors. Depending on whether the sorbent is attached to the board by means of an adhesive or freely sprayed evenly on the board. TLC methods are distinguished in the fixed and non-fixed layer of the sorbent. Such balls can be used several times. After each chromatography process, the plate is cleaned of organic matter in the chromium peak mixture and heated in the thermostat to make it suitable for further analysis. However, such balls have not been widely used. Two-phase balls are sometimes used in pharmaceutical and biochemical analysis. The sample mixture which rises to half of the plate is first cleaned of foreign matter, then in the second half of the plate it is separated by advancing with another solvent. Also, the samples are arranged in a circle on the starting line. Chromatograms can sometimes detect spots with an unwanted tail rather than a circle. The reason for this may be placing the sample on the starting line in excess of the load capacity of the board. In this case, dilution of the sample is recommended. During the chromatography process, the temperature change or inner saturation change in the chamber. This problem may be due to the camera lid being opened during the chromatography process, for a transport of the sample by mobile phase or element. This can be observed in high molecular compounds, for example proteins, or in compounds with a large number of functional groups. To prevent this, the polarity or pH of the element must be changed. Sample quickly transported by a mobile phase. In this case, the substance cannot balance with the solvent. It can be prevented by changing the polarity, mobile phase or pH. The solvent should be chosen as a sample solvent when it completely dissolves the sample and can be removed from the plate as soon as possible by evaporation. When working with high boiling solvents such as dimethylpharmamide or dimethyl sulfoxide, evaporation of these solvents from the plate will result in a certain loss of time. In the descriptive analysis, the diameter of the sample spot at the starting line should not exceed 5 mm. And in the quantitative determination, this figure should be slightly smaller. Otherwise, the stain may be enlarged when the sample is lifted by carrying the solvent. The solvent system begins in a rise along the solvent on the plate due to capillary forces in the form of rising chromatography. In the form of vertical chromatography, vertical elevation is carried out by transferring the solvent stream to the chamber. When the solvent rises, they also try to leave the sample mixture placed on the starting line by them. When the solvent system reaches the boundary line is marked on the board. Then the plate is removed from the chamber, dried under a stream of warm air until the solvent vapors are completely removed and prepared for chromatogram detection. Once the chromatography process is complete, the chromatogram needs to be prepared for detection. For this purpose, the plates moistened with the solvent system are dried under a stream of warm air until the solvent is completely removed, until the solvent odor is completely gone. In the absence of special interactions, UV irradiation of wet balls can lead to chemical conversion of substances. Detection of colored substances can be carried out by absorbing UV rays, fluorescence, and color chemical reactions. Detection by color chemical reactions provides significant advantage to the TLC analysis methods. Such color reactions are especially important in screening analysis. To perform the chemical reactions with chromatograms, the plates are either immersed in the reagent solution, kept under the reagent vapors, or the detective reagents and sprayed on the chromatogram using special sprays. Screening is a series of systematic research methods that allows samples to be analyzed based on scientific experience, identifying them first in groups and then individually, by selecting samples from different substances. The purpose of the screening analysis is to obtain and investigate the maximum results of negative and positive indicators in a short period of time. Screening designed to identify multi-component mixture and unknown substances. Reagents are divided into universal reagents for all groups of substances, group reagents for certain groups, for example barbiturates or benzodiazepines, and specific reagents for individual substances. In the detection of neutral and weakly based substances, IR-A of the chromatogram is firstly examined under UV light and then subsequently treated with the detector reagents. Hydrogen sulfide plus 0.1% diphenylcarbazone solution, heating, then 10% iron chlor 3 solution, Dreigendorf reagent, heating, then Brayton-Marshall reaction. IR-B on the chromatogram is treated with a one solution of with vanillin in methanol to determine meprobamate. Zone 1 and 3 to 3 of IR-C on the chromatogram is eluted with methanol. Sequence of detection of basic and weakly base substances. Irradiation after 10% iron chlor 3 solution, then 57% chlorous acid, then 0.5% natrium nitrate solution, then the Dreigendorf reagent, then Brayton-Marshall reaction. Zone first of area is eluted. High-performance liquid chromatography. HPLC was formerly known as a high-pressure liquid chromatography. However, since pressure is not a feature of the process, but only the flow rate of the mobile phase movement, it is now preferable to call the method HPLC. HPLC refers to columnar liquid chromatography methods and is used to separate the components of the mixture, separate the individual component, identify and quantify the mixture. The HPLC method separates the component by passing the liquid eluent used as mobile phase through a sorbent-filled column under stationary phase pressure. In a sense, the HPLC method is the modern version of the classical columnar liquid chromatography method. High-speed analysis, minimal washing of chromatographic zones, high separation capabilities, separation of thermally liable components in their components, complete automation of the process, and adds. Positive features such as these allow applying the modern methods of HPLC to all areas of pharmaceutical analysis. The chromatogram consists of several models. A tank filled with solvent eluent, a mixture of mixed solvents, a pump to ensure the flow of eluent with pressure, an injector for injecting samples into the system. The gas-liquid chromatography method is used for separation, characterization, and quantum analysis and volatile thermostable chemical compounds. These mixed sample molecules, which are converted to volatile vapor by temperature under the influence of the methods, are identified by splitting into consistent components without decomposition. The gas chromatography uses a chemical inert gas or mixture of gases called a gas carrier, such as mobile phase. The method is a type of distribution chromatography. Here, stationary phase is liquid and mobile phase is gases. The main condition required for the application of the method is the volatile of the components of the sample mixture under study and their resistance to the operating temperature of the column. The sample components are separated as a solution in different areas of the liquid phase according to the distribution coefficient as it passes through a column containing a liquid with a high boiling point in the form of stationary phase in the form of gas. In this case, the component with the worst solution in the liquid phase leaves the column first, then the other component with the best solution. The GLC method has many positive qualities. With the help of the GLC method, it is possible to analyze both qualitatively and quantitatively compounds with close chemical composition, the boiling point of which is slightly different in complex mixtures. Very few samples are required for analysis, and the analysis takes only a few minutes. In stationary liquid phases, the absorption isothermal line under normal operating conditions, and the chromatography peaks are recorded symmetrically. It is possible to adjust the storage parameters and the resolution of the separation by easily changing the amount of the stationary liquid phase. When NL is used as a standard, the retention index is called the Kovats retention index or Kovats index. The numerical index of the Kovats index doesn't depend on the conditions of chromatography division and has a constant value for members of the homologous series. The basis for the identification of the components for the sample with the Kovats index is a linear relation between the logarithm of the corrected retention volume and the number of carbon atoms in a normal hydrocarbon molecule. Kovats index is determined by calculation graphically or by formula. Spectral analysis. Spectral analysis is a combination of methods for determining, purifying, and quantifying electromagnetic radiation based on the study of the absorption, emission, luminescence, reflection, and scattering spectra of substances. Spectroscopic analysis methods study the physicochemical properties of change in matter on the basis of general laws by irradiating the sample with electromagnetic waves. The sequence of signals recorded graphically by spectroscopy methods is called a spectrum. The determination of signals in the spectrum depends on the properties of the electron clouds of molecular and atoms, the excitation states of atomic nuclei, the vibrational motions of bonds in molecules, and so on depends on the processes. Based on this, spectral analysis covers a wide range of wavelengths, from X-rays to microwaves. Electromagnetic waves are not used in mass spectral analysis. The electromagnetic spectrum ranges from gamma rays to radio rays. Ultraviolet and visible spectroscopy are also called electron spectroscopy because they study the electronic transition between valence molecular orbitals. With the help of the methods, the electronic and spatial structures of molecules, tautomerism, dissociation constants of acid and bases, kinetic parameters of the reaction, intermolecular and intermolecular energy conditions, and as studied. There is a relation between the change in the intensity of light passing through the medium and the concentration of substance in that medium, the law which is called Fourier-Lambert's law. The absorption spectrum refers to the absorption depending on the wavelengths. The absorption of light by the solution is selective. At certain wavelengths, the absorption intensifies. At some wavelengths, the absorption doesn't occur. IR-Spectroscopy is a widely used analytical method based on the absorption of electromagnetic waves and is successfully used in toxicological chemistry in the study of the chemical structure of substances, their characteristics, and quantification. With the help of IR-Spectroscopy, various functional groups in the molecule are quickly and accurately determined. Carbonyl, carboxyl, hydroxyl, single, double, triple, amides and amines, cyanide, eds. It's also possible to accurately identify the paths of molecule with unsaturated bonds, double and triple bonds, aromatic paths. IR spectroscopy are also always the study of intermolecular and intermolecular interactions. Mass spectrometry methods is based on the study of the ratio of the positive and the negative ion masses. formed in the gas phase after the conversion of the studied chemical compound into ions according to the Laud ratio. Unlike other spectroscopy methods, mass spectrometer doesn't use electromagnetic waves in the analysis, but because of its closeness to spectroscopy methods due to its many features, this method is studied among spectroscopy methods. Mass spectroscopy is characterized by the separation of matter into ions in an electric or magnetic field. Mass spectroscopy is more sensitive than NMR and IR-Spectroscopy. Nuclear magnetic resonance spectroscopy is a method of studying the properties of a molecule in a magnetic field as a result of the resonance absorption of electromagnetic energy by the atomic nuclei that make it up under the influence of radio frequency waves. In other words, NMR spectroscopy records energy level transitions that occur in atomic nuclei under the influence of radio frequency waves. With the help of NMR, the chemical structure of organic compounds, including the primary, secondary, and absolute structure of substance. Thank you very much.